Okay, so we're going to be talking about polynomial functions today, and the first thing we're going to do is classify polynomial functions. When classifying a polynomial function, I guess we first need to understand what a polynomial function is. Alright? A polynomial function has distinguishing behaviors. You can look at it in algebraic form and know something about its graph. You can also look at its graph and know something about its algebraic form. So a monomial, let's highlight this lovely vocabulary word, is a real number, a variable, or a product of a real number and one or more variables with whole number exponents. The degree of a monomial in one variable is the exponent of the variable. All right, so for example, if you have this 3x squared as your monomial, your degree of your monomial is 2. This is a second degree monomial because your exponent is a 2. All right, a polynomial is a monomial or a sum of monomials, so monomials added together. The degree of a polynomial in one variable is the greatest degree amongst the monomial terms. So, what I have here in the box at the bottom of the page is a monomial, or a polynomial. So you can see here, polynomial p of x. I love p of x for polynomial functions. And then all of this mathematical verbiage here. All this means is you're going to have x to your highest power here, next highest, and so on and so forth, x to the 1 power, and this is just a constant with no variables. Now, when you are writing a polynomial function, one thing you need to know about it, and you see that in this example here of a polynomial function, the highest power term always comes first, then the next highest, then the next highest, and this, your constant, is last. Now, each of these terms has a name, and the name is based on the power of x. So, if you have a number with no x at all, this is called a constant term. When you have x to the power of 1, that is your linear term. Okay? And remember, a linear function, y equals mx plus b. If you have x to the second power, that is your quadratic term. And if you remember this, y equals ax squared plus bx plus c as a quadratic function. Notice, x to the 1 power, x to the 2 power. Right here, x to the 3rd power is called a cubic term. All right, we're going to be working with some cubic functions today. Also some with some higher powers. So the next thing that we're going to do is I'm going to flip the page here, and we are going to explore how you name a polynomial based on both the number of terms in the polynomial, 1, 2, 3, 4, or more, all right, and the degree of the polynomial. So I love this table here. It is super awesome. It is sorted by the degree of the polynomial, which is the highest power of x. Okay? The name for that degree, an example of a polynomial of that degree, the number of terms in that polynomial, and the name of that polynomial based on the number of terms. So every polynomial has two names, a degree name and a number of terms name. So every polynomial we're going to give one of each of those names to. So for example, degree 0 is a constant. Here's an example. It has one term. See, there it is. We call it a monomial. Degree 1 is a linear function. Here is an example. This one has two terms. We call that a binomial. Degree 2 is called quadratic. Here is an example of a quadratic. This only has one term though. See, one term. Therefore, it is a monomial. Right here, degree 3 is cubic. That means you're going to have x to the third power as your highest power. And you see right here you have it. We have 1, 2, 3 terms. See right here, 3 terms. This is called a trinomial. All right? Fourth degree is quartic. All right? Here is an example of a quartic function. It has x to the fourth as its highest power. We have 2 terms here. C2, this is a binomial. This one's interesting. 5th degree polynomial. This is called quintic. Quintic. See here, x to the 5th. Lovely. 1, 2, 3, 4 terms. After we hit 3 terms, it's just called a polynomial of however many terms. So this is a polynomial of 4 terms. So if we go down here to example 1, we're going to classify some polynomials. So first thing it says is write each polynomial in standard form. And then what is the classification of each polynomial by degree and by number of terms? So first of all, in standard form means highest power of x first, then next highest, next highest, next highest. So this is going to be 9x squared plus 3x plus 5. What's the degree of this polynomial? 2, which makes it quadratic. Now, how is it named based on the number of terms? Trinomial. So this is a quadratic trinomial. Over here, wow, what a mess. We've got to put these in order to make it be in standard form. So we're going to put x to the 4th first. I don't have any x to the thirds. Look, I have 2 terms that have x squared, so I need to combine those like terms. So plus 4x squared. Then I've got plus 4x and then minus 12. What is the name for the degree of this particular polynomial? Quartic. 4th power. 4th power, so this is quartic. And 4 terms gives us what name? Yes, quartic polynomial of 4 terms. Okay, next thing we're going to get to is graphing. So, let's go down to the bottom of the page here. And we have a little bit of a paragraph or 2. We are going to be graphing polynomial functions and describing end behavior. All right? Do you remember when we were doing, let me give us a nice little graph here. We were doing parabolas, right? And we could have something like this, right? And this is quadratic. End behavior means where do these go? The ends. And it's different for different polynomials. But what we're going to learn how to do today is determine where those ends are going to go, off to positive infinity or off to negative infinity, based on looking at the equation. We know this is quadratic. As long as a is positive, these are going off to positive infinity on the y-axis, okay? So what we're going to do is learn how to do this for polynomials. So the degree of a polynomial function affects the shape of its graph and determines the maximum number of turning points. Now, I will tell you, this right here is what we call a turning point. A turning point is where it switches from going down to going up, or where it switches from going up to going down. All right? So that's what a turning point is. Or places where the graph changes direction. It also affects end behavior, or the directions of the graph to the far left and the far right. So what we're going to do is flip the page here, and we're going to talk specifically about a few polynomials. Lovely chart here. Okay. Let's go right here. This is quadratic, right? Okay. Let's put a little note by this. This is quadratic. And this one has a negative sign in front of x squared, so it's concave down. So look at, the end behavior is down and down. See what I'm saying? This one has a turning point at 1, 1. That's right here. Put a little arrow. This is a turning point. The function is increasing when x is this is where x is 1. When x is less than 1, it is increasing. When x is greater than 1, it is decreasing. So right here, increasing, decreasing. You always look at this as you're going from left to right. Okay? The next one I'm going to show you, it's a little bit out of order, is go down here to this one. This is cubic. And this is actually the cubic parent function, y equals x to the third. Notice what this looks like. All right? The end behavior is down and up. All right? This guy has no turning points. I'll tell you, the maximum amount of turning points is 1 less than the degree of the polynomial, the maximum amount. So the maximum that this could have is 2, and some cubic functions have 2, but this one doesn't have any. It is going up, still going up, always going up, never goes down. So the function is increasing for all x. Now if we go over here to the right, this is another cubic function. What's important to notice is that this time our a value is negative. So notice our end behavior is reversed. Instead of being down and up, it is up, then down. All right? All cubic functions that have a negative x to the third value are going to be up, then down. All of them. All right? Now, in this particular one, we've got some turning points. We have a turning point here and here. We will talk later about identifying turning points. To be honest with you, the easiest way to identify a turning point is to make it to calculus, because it is super easy to do it in calculus. A little bit more difficult for us without calculus as a tool. So it is telling us that these are our turning points right here. This is something that, believe it or not, we can get from our graphing calculator. Now keep in mind, the function is decreasing right here. See, it's going down. At this turning point, it is increasing. From here to here, it is increasing. Always think, where am I going from left to right? As I continue going right, I am now decreasing. So I was decreasing, increasing, decreasing. So it's going back and forth. All right, let's go up here to the very top. This x to the fourth is quartic. Now quartic is up and up. If the a value in front of x to the fourth were negative, it would be down and down, just like the quadratics. Now notice something, this is true. If your degree is an even degree, your end behaviors are going to be the same. If it's a positive coefficient, it'll be up and up. If it's a negative coefficient, it'll be down and down. What it has to do with is the number of bumps in between the ends. Notice, one bump in between the ends. Here at x to the fourth, we've got two bumps between the ends. This bump and this bump. So as we go up in terms of degree, if we get up to x to the sixth, it'll still be up and up, but we will have three bumps. All right, we can actually play around with our graphing calculator and make some functions up and see what these look like. With this particular one, we've got a couple of turning points. This, and this. We'll put little arrows here. These are our turning points. And these are where we go from increasing to decreasing and decreasing to increasing. So notice right here, decreasing, increasing, decreasing, increasing. So we're going up and down, up and down. All right? So all we're going to look at to determine our end behavior is our first term of our polynomial in standard form. So let's go down here to example 2. Consider the leading term of each polynomial function. What is the end behavior of the graph? So first of all, what kind of function is this?
Quadratic.
This is quadratic. Quadratic, even power, so it's either up, up, or down, down. All right? This has a positive coefficient in front of the x squared, so this is up, up. All right? If we go to b, I've got x to the fourth. It's an even power, so we know it'll be the same. The question is it up, up, or down, down? This is down, down because we have a negative coefficient, so this one's down, down. Okay, lastly here, we have negative 4x to the third. This is an odd power. This is cubic, so it's going to be 1 up, 1 down. Since there's a negative in front of here, what comes first, the down or the up?
Up.
Down.
Down. First it's coming down, then it's going up. So keep in mind, it's just like this example here at the top of the page. Negative in front of the x to the third power, it's first up. Whoops. I guess you guys are right and I'm wrong. Up, and then it's going down. I'm thinking increasing and decreasing. It's first up, then it's going down. All right?
Wait, why? Why?
Because don't you read it from left to right? So
It's decreasing, but it's up. The end behavior is up. It is decreasing. When it's up, it's decreasing. Because you're reading from left to right. And look at the difference. When the x to the third term is positive, it starts down, then goes up. When it's negative, starts up, then goes down. All right? You've got to keep track of the difference. Now, when you get to like x to the fifth, which is also odd, it'll be alternating. It'll be down, up, and up, down, depending on whether your coefficient is positive or negative, but there will be bumps in the middle. It actually is pretty cool. Okay, so we're going to go ahead and we're going to graph some. All right, first of all, what is the graph of each cubic function? Describe the graph including end behavior, turning points, and increasing / decreasing intervals. So first of all, this guy here is, notice, it's really close to our parent function, right? Because our parent function is y equals x to the third. We have a 1/2 in front of it. Guess what translation that is? That's your A value.
stretch. Vertical compression.
This is vertical compression. Your A is between 0 and 1. This is a vertical compression of the parent function. So here's the first thing we're going to do. We've got to do our end behavior, and our end behavior is down, up. So it's going to do something like this. That's what our basic shape is going to look like. All right? So a good thing for us to do to make some points is to make a table of values. Whoops. Let's put our x right here. Let's put our y equals 1/2 x to the third. Let's put a 0 in there. And so what does y equal? 1/2 0 to the third equals 0. So 0, 0 is a nice point right on our graph. Okay, let's put in a 1. So 1/2 times 1 to the third, 1/2, right? There we go. How about 2? So 1/2 times 2 to the third, that equals 4. 2 to the third is 8. Half of that is 4. Going up really fast. So you can see right here, this is following exactly what we said it was going to do right here, which is go up. We need to go do the other side of this. So we're going to do -1. So 1/2 times -1 to the third power is -1/2. That's right here. And let's do another one, -2. So 1/2 times -2 to the third power, that's -8. And then multiply by half gives us -4. Right there. And you'll see it's going down. This particular one does not have bumps. All right? It is increasing the entire time. It is always increasing as you go from left to right. Always increasing, no bumps. So no bumps or turning points. In order for a cubic function to have some bumps and turning points, it's got to have some more stuff here. And that's what will create it. So let's go down here to the second example, which I think we may find has a little bit of a bump to it. All right, so first thing we're going to do, let's put this in standard form for goodness sake. So this would be -x to the third plus 3x. Would you agree? Now, based on this term right here, what is our end behavior going to be? Up, down, all right? So it's going to be up, down, which means something like this. Maybe some bumps in there somewhere. So it could be like that or like this, all right? Some bumps. One or the other, something like that. It has that general shape to it, so we're going to find out. First thing we're going to do is let's find ourselves a few points. So x, y equals -x to the third plus 3x. So I love putting 0 in there. So -0 to the third power plus 3 times 0 gives us 0. So we've got a point right there. All right. I'm going to put in 1. So -1 to the third plus 3 times 1. Would you agree? That gives us 2. So I've got the point 1, 2 right there. Okay. Let's go 2. So -2 to the third plus 3 times 2. So this is, let's see, -8 plus 6. Wouldn't that give us -2? Okay. So 2, -2. Oh, so do you see a bump there somewhere? Just a little one. All right, so now we're starting to see the shape of this thing. It looks like it's doing something of that sort. Let's go to the left. So put -1 in. -1 to the third plus 3 times negative 1. So this is going to be 1 minus 3 gives us negative 2. Right there. And let's do negative 2. So negative 2 to the third plus 3 times negative 2. So this is negative 8. The negative of that is positive 8. Minus 6 gives us 2. So we've got negative 2, 2, which is way up there. So you can see something like that. So just based on our like silly little drawing, it kind of looks like we have a turning point here, right? All right, so let's identify turning points. How about 1, 2? That's this point, and negative 1, negative 2, that's this point. What else do we need to identify? Increasing and decreasing? Okay. So, when x is less than negative 1, that's here, it's decreasing.
Can you move it up a little bit?
Sure can. Between negative 1 and 1, so remember how to write this from many chapters ago, it is increasing. And then when x is greater than 1, it is again decreasing. So just playing around with these are kind of fun.